In this video, we consider two independent samples under the assumption that the two population standard deviations are unequal. Then we have to use a different test statistic, this test statistic. If you compare it to the test statistic under the assumption that sigma 1 is equal to sigma 2, then you see that there is a difference here. Instead of the pooled sample variance, sp squared here and sp squared there, we now just sum the sample variance of the first sample divided by n1 and the variance of the second sample divided by n2. When the samples originate from a normal distribution, or when n1 and n2 are large enough, that is greater than 30, then this test statistic has a t-distribution under the null hypothesis. And this t-distribution has n tilde degrees of freedom. And I write n tilde here because it's not so easy. You could compute it with this. That's a bit much and not really necessary. In practice, of course, you would use R, but if you do the exam and there's no technology available, then you are allowed to use this approximation, to use that n tilde is approximately equal to the minimum of n-1 and n-2. On your formula sheet, you will also find this formula and that formula. Not this one, we will not use this formula. Again, we can also use this to construct a 1 minus alpha confidence interval for mu1 minus mu2. The idea is the same, the difference of the means minus the margin of error and plus the margin of error. But now in this case, the margin of error is equal to the t-score, which you can find in the table at n tilde degrees of freedom and a significance level of alpha over 2 times the standard deviation again. So in this case, that is s1 squared divided by n1 plus s2 squared divided by n2, just as in this formula for the test statistic. Let's do an example. We want to test the claim that males and females have the same mean BMI, body mass index. Step 0 is to indicate the population parameter. Well, we have two samples, a female sample and a male sample, and our population parameter is mu1 minus mu2, the difference in mean BMI of females, that's mu1, and males, mu2. We will now formulate the null and alternative hypothesis. The null hypothesis states that mu1 is equal to mu2, and by the test claim saying that males and females have the same BMI, the alternative hypothesis is that mu1 is unequal to mu2. And suppose that in this exercise we have a significance level of 5%. We have a look at the data. We have 40 females and 40 males in this case, and we know the means of both samples and the sample standard deviations. We now check the requirements. We assume that these samples are independent and that sigma 1 is unequal to sigma 2 because the sample mean here is 5.36 and the sample mean here is 7.39. It's not reasonable to assume that these population sample means are equal. Furthermore, we see that both samples are large enough. They both contain 40 data values. So now we can go to step 3. Because of our assumption that sigma 1 is unequal to sigma 2, we use this test statistic. We approximate the degrees of freedom by the minimum of n1 minus 1 and n2 minus 1, which is both equal to 39. Which means that this test statistic approximately has a t-distribution with 39 degrees of freedom under the null hypothesis. We can now compute the observed value of the test statistic. We can compute this value by the data that we have, and under the null hypothesis, mu1 minus mu2 is equal to 0, and we can also compute the square root of the square of the sample standard deviation of the first sample divided by the size of the first sample plus the square of the sample standard deviation of the second sample divided by the size of the sample. Then we see that this observed value of our test statistic is approximately equal to negative 1.275. This is a two-sided test, so we again go to table 3 and we look at 39 degrees of freedom and at the significance level of 0.05 in two tails. Then we find this t-value, and because this test is two-sided, the other half of this critical region is less than or equal to the negative version of that t-value. But we also see that our observed value is not contained in this critical region, so we cannot reject the null hypothesis. There is not sufficient evidence to reject the claim that males and females have the same mean body mass index. We could also compute a confidence interval for the difference in means of the male and the female sample. Suppose we want a 90% confidence interval. This confidence interval is based on the point estimate of the difference in mean BMI of males and females, which is estimated by the difference of the sample means. Then to find our 90% confidence interval, we have to compute the margin of error, and tilde is still equal to 39, and alpha over 2 is 5% in this case, because we want a 90% confidence interval. We already computed this square root, but now you must go to the table 3, and find this critical value. So you look at 39 degrees of freedom and then at an area of 0.05 in one till, and then you will find this value. Then times the square root and you find approximately this margin of error, so that means that our 90% confidence interval is equal to our point estimate minus the margin of error for the left bound and our point estimate plus the margin of error for our right bound. So this is the 90% confidence interval for the difference in mean body mass index of females and males. In R, you can use the command t.test to perform a t-test. If you substitute two samples here, then by default, R will perform an independent sample t-test under the assumption that the two population standard deviations are unequal, which is in this case a reasonable assumption because sample 1 has this standard deviation and sample 2 has that standard deviation. Also, by default, the test tests the alternative hypothesis that the true difference in means is not equal to 0. So, by default, this is a two-sided test. The test returns the value of your test statistic, the number of degrees of freedom, which is not an integer, as you can see, and that is because of that complicated formula that we don't use. And it also returns the p-value. So, if your significance level is 5%, then we would reject the null hypothesis. It also returns a 95% confidence interval, and it returns your two sample estimates. So it gives you a lot of information. If you want to perform the t-test under the assumption that the two population standard deviations are equal, then you have to add this to your command, that var.equal is true. That will change your test statistic. Now the observed value is equal to this. The test statistic has a t-distribution with 68 degrees of freedom, and our p-value is equal to 0.0785. So now we would not reject if our significance level was 5%. Let's do a short recap and remember that all formulas on these slides will be on your formula sheet at the exam. Suppose we have paired samples from populations with population means mu1 and mu2. The two samples here are dependent, and we are going to perform a test about the means of these two samples. Therefore, we compute the differences between the paired values, d1, d2 up to dn, and we compute the observed sample mean, d bar, and the sample standard deviation, sd. Then the test statistic that you have to use to test the hypothesis about the difference of mu1 and mu2 is equal to this. The sample mean of the differences minus mu1 minus mu2 divided by the sample standard deviation of the differences over the square root of n. This has a t-distribution with n minus 1 degrees of freedom under the null hypothesis. A 1 minus alpha confidence interval for mu1 minus mu2 is given by the observed sample mean of the differences minus the margin of error, and on the right side plus the margin of error, where the margin of error is equal to the t-value at a significance level of alpha over 2 for a t-distribution with n minus 1 degrees of freedom times the standard deviation of the differences divided by the square root of n. This is about dependent matched pair samples. This is the independent case. We consider two cases: the case where the population standard deviations are equal and the case where they are not equal. In case you can assume that they are equal, then we use this test statistic. which is based on the pooled sample variance, which you can compute by this formula. Under the null hypothesis, this test statistic has a t-distribution with n1 plus n2 minus 2 degrees of freedom. In case it's not reasonable to assume that the two population standard deviations are equal, so now we assume they are unequal, then you have to use this test statistic. This has, under the null hypothesis, approximately a t-distribution with n tilde degrees of freedom, which we compute if we have no technology available by the minimum of n1 minus 1 and n2 minus 1. The 1 minus alpha confidence interval is given by the difference of the sample means of the two samples minus the margin of error and plus the margin of error for the right bound. This margin of error is equal to this in case that you can assume that sigma 1 is equal to sigma 2. And it's equal to this in case you cannot make that assumption. So in case sigma 1 is unequal to sigma 2. Again, you don't have to remember these formulas, but you have to know when to use what formula.